you know, sometimes we are not interested just in population mean, but we are interested in population variance. And we want to estimate the population variance. As you can think, oftentimes in cases when you're dealing with quality control and things like that, what is of interest to us is the variance, and we want to estimate the variance sometimes. So when we are dealing with that, then we use the so-called chi-squared, which we have already discussed it in a few chapters ago. That was, you know, probably 2 months ago or something like that. We go a little bit deeper into it. So as you guys remember, chi-squared was for the variance. And again, let's take a look into the terminologies, or, you know, into the variables. S square is obviously my simple variance. Sigma square is the population variance. And n minus 1 is, so n is essentially my sample size, right? And we have a chi-squared distribution. So we can apply that whole null hypothesis, alternative hypothesis stuff that we did for the population mean. We can do the same thing, of course, for the population variance as well. As I mentioned, so the formula that we use is here a chi-squared formula. So chi-squared equals n minus 1 times s squared divided by sigma squared. As you remember, n minus 1 was the degree of freedom. S square is the variance of the sample. Sigma square is the variance of the population. So we can take a sample to estimate the variance of the population. Just like with the mean, whatever is the variance of my sample is essentially my point estimate, and then I build a 95% confidence interval around it, or 90%, or whatever I have. I have build my confidence interval around it. I can also use chi-squared for doing hypothesis testing on variance, essentially. Okay, so let's do some examples. We have a container filling machine that's used to package a variety of liquids, so stuff like milk, soft drinks, and paint. Ideally, the amount of liquid should vary only slightly, since large variations will cause some containers to be underfilled and some to be overfilled. If you have a high variance, then, you know, some bottles are, you know, too empty, some bottles are too full, so you have a problem. The president of a company has developed a new type of machine. So you own this factory, so some company that produces these machines, he says, hey man, we have this new machine and it fills 1,000 cubic centimeters, which is 1 liter, so accurate that the variance of the fills is less than 1 cubic centimeter. You think to yourself, wow, that's amazing. So to do a hypothesis testing kind of, you know, hypothesis testing, you take a sample of, I believe it was 25 bottles, and on each bottle you measure exactly how much is the bottle filled with that new machine that, you know, he's claiming is super accurate. And we want to see if his claim is true at a 5% significance level, which means my confidence level is 95%. So what is null? What is alternative hypothesis? Keep in mind, when you are not sure, just take the status quo as a null hypothesis, right? So status quo is that machines are not super accurate. So the variance is larger than 1 cubic centimeter. Alternative hypothesis is that, you know, new claim that it says, nope, it's less, at least with this new machine, it's less. We want to figure it out. So first of all, we set up the null and alternative hypothesis. The null hypothesis is that it's larger than 1 cubic centimeter. So from 1 cubic centimeter, and then the theoretical limit would be infinity. If it's between 1 and infinity, again, as I said, we take the value that's closest to the alternative hypothesis. Since the alternative hypothesis is that sigma square is less than 1, we take the value of 1 for the null hypothesis, right? Because the null hypothesis is that it's larger than 1. So we just take the 1 for the null hypothesis. For alternative hypothesis, we take the value, you know, it's just smaller than 1. Since we are not dealing with beta here, we don't need to do any calculations for beta. We don't need to assume any concrete value for alternative hypothesis. It's enough to have it here as smaller than 1 cubic centimeter. Now, what kind of a test is this? Left tail, right tail, or two tail? You see it here. It's a left tail test, right? So it's a one tail test. To be more concrete, it's a left tail test because it's a smaller than 1. And our test statistic, the formula that we use is obviously this one here, chi-squared equals n minus 1 times s squared divided by sigma squared. The 25 bottles had a total of 24,992 cubic centimeters. X squared is this value. So we can use the formulas that we learned in, I don't know, chapter 3 or something like that to calculate the average variance. And the average variance in our sample is 0.633333. So it is less than 1 cubic centimeter. So that is good. But is it so far less than 1 cubic centimeter that gives us enough evidence to reject the null hypothesis with a 95% level of confidence, right? So that's the question here. We insert the values essentially here in the formula, okay? And what we have is 25 minus 1, so my sample size was 25. The calculated variance in my sample is 0.63333. And for sigma square, so sigma square is my population variance. Of course, we don't know the population variance. So just like with mean, when we are dealing with mean, the value that we take is the value from our hypothesis, in this case, the null hypothesis, okay? And the null hypothesis was like, hey, population mean is 1 cubic centimeter. So just we entered that because, we're dealing here with alpha, remember? So we have to use the population variance of the null hypothesis. If we calculate it, we get a 15.2 value for the test statistic. Okay, so my sample gave me a chi-squared of 15.2. So essentially, you have to imagine it this way. If you look on the top of the table 5 in your appendix that is dealing with chi-squared, you see like a kind of a shape of it, a typical shape. As you know, it's not symmetric chi-squared, okay? So that's my chi-squared distribution, okay? It's essentially a left tail test. We have essentially a null hypothesis and an alternative hypothesis, okay? And then we are looking for a threshold value, okay? And what we just calculated here is essentially that 15.2 was the value for from our sample. Our sample gave us a value of 15.2. Now, is it on the right side or is it on the left side of the critical value? We don't know. So that's why we need to kind of figure out what is the value here for our critical value. CV for critical value, right? What is it? And that's what we try to figure out. And in order to do that, we need to simply look into the table. It is a left tail test. Keep that in mind. So it's not a two-tail test. If it was a two-tail test, we would have to divide the alpha into two pieces, etc. But we don't need to do that here because it's a left tail test. And we were having a, I believe, was it 95% level of confidence that we wanted to achieve? I think it was 95% level of confidence. So we have to look it up into the table. So if everyone goes again into table 5 of the appendix, where it says critical values of the chi-squared distribution, okay? And so our sample size is 25, which means that our degree of freedom is 24. So first we look here into the column to the left for the degree of freedom, 24. That determines essentially in which line we have to look for, okay? Now it gets a little bit tricky. Look, we had essentially the null and the alternative hypothesis. It was a left tail test, right? So we want to see the 5% that we were looking for is supposed to be to the left of the critical value. But if you see that critical value that we get here, look at the picture on the top, the green area is to the right. So whatever value this is giving us is to the right of the critical value. So if I take the critical value here for 5%, if I look into this column, I'm doing the wrong thing because it means that 5% is to the right and 95% is to the left. What I want is the opposite. This is a left tail test, so keep that in mind. So because of that, I would have to look here for the critical value chi-squared of 95% and not of 5%, okay? So that's why I always told you when you use these tables, always look on the picture on the top, see what it's showing and compare it in your mind with what you're looking for, okay? We are looking for the critical value of 5% on the left tail test, right? So we have to look here for 95%. And if you go down, it's 13.8, right? So 24, degree of freedom of 24. And then you see it's 13.8 for 95%. Anyway, long story short, We had discussed that actually a month and a half ago when we did chi-squared, but you know, I'm guessing that some of you guys might have forgotten it, so doesn't hurt to repeat. Okay, so 13.85 or 13.8 or whatever is that value. And 15.2 ends up being not smaller than that, it's larger than that. So what we figured out is that, hey, based on our sample, that evidence is just not enough to reject the null hypothesis with a 95% level of confidence in favor of the alternative hypothesis, right? You see, our mean is smaller than 1 cubic centimeter, right? It is smaller, it's 0.633, but it's not, you know, far enough to say that, okay, this cannot be just a regular anomaly, right? So it might be that the variance in reality is 1%. If that is the case, it's still pretty likely based on the sample size that we took and based on the variation that we observed in the sample, that, you know, you end up with a sample of 0.633. So it's just not enough at a 95% confidence level. If it was a 90% confidence level, maybe it would have been enough, right? But not for a 95% confidence level. Oh yeah, so what we can also do is we can also go after the question to estimate with 99% confidence the variance of the field. So how much is the variance of the field actually? And we need to estimate it with the 99% confidence. So this works also the same as before. So our mean was a variance of 0.633, right? And we need to build an interval where with 99% confidence, we can say, you know, we have a lower confidence level and the upper confidence level, where we can say the variance is going to be between these values with 99% confidence. Okay, so we have upper confidence level and lower confidence level. Something changes here though, keep that in mind. And what changes is if you look into the distribution, it's not symmetric anymore. It's not like student t distribution or z-score where you had something symmetric. Here, it's not symmetric. It looks, you know, if you remember, it cannot be smaller than 0. So there's a theoretical limit, but to the top, anything, you know, theoretically, it can go into, you know, infinity. So it is skewed to the right, okay? Which means that the distance from my lower confidence level to my point estimate will not be the same as the distance of my upper confidence level to my point estimate, okay? They're gonna be different. Before, it was always the same. Z-score, T-score, it was always the same distance. You would go, I don't know, 2 standard deviations to the left and then 2 standard deviations to the right, and, you know, it would work. But here is not the same thing. As you can see, the table, it doesn't have just the value for 1%, it has also the value for 99%, and so on and so forth. It has the value for 2.5%, but it also has the value for 97.5%. Why? Because it's not symmetric. So keep that in mind. Now, the way we calculate that is here. You see, for example, chi-squared, since we are having a 99% confidence level, it means we essentially we take 0.5% to the left and 0.5% to the right. Those are essentially the tails that we cut off, okay? And 0.5% to the right, and then 0.5% to the left. So essentially, yeah. So this value is my you know, upper, lower, and upper confidence levels. So we plug them in. We know that chi-squared has to be 45.6. N minus 1 is, our sample size was, I think, 25. So 25 minus 1 is 24, multiplied with S squared. How much was S squared? Oh, 0.63333. Yeah, 0.633. So what we are looking for are these values here, essentially. Sorry, here, these values here, the lower confidence level and upper confidence level. So this is 0.633333. You multiply it with 25 minus 1, which is 24. And if you do the math, it's going to be 15 point, what is this, 15.2? 15.2. You divide it by that chi-squared value that we calculated. So it's 0.33333. Okay, that's the lower confidence level. And same thing Same calculation here for the upper confidence level, we get 1.537. Now let's take a close look. So essentially my lower confidence level is, now I have a value for that, 0.333. That's the variance of the machine, lower confidence level. And the variance for the upper confidence level is 1.537, which is, well above that 1 cubic centimeter. And that is why in the previous question, we were rejecting the alternative hypothesis, even though our our sample variance was 0.63333, right, which is below one cubic centimeter. But when we build that 95% or 99% estimate for the population variance, we see that, okay, chances of it being over 1 cubic centimeter, if you assume that here this is the limit for 1 cubic centimeter, chances of being above that is still pretty high. And that was why it wasn't enough for us, even though having a sample variance of 0.633, to assume with 95% confidence that the machine's accuracy is indeed below 1 cubic centimeter. And as you see, it is by no means are the distances the same, right? So from 0.3 to 0.6, it's 0.3 is the distance, but from 0.6 to 1.5, it's about 0.9 is the distance. It's by no means the same. Why? Because of the distribution. As I mentioned, it's kind of like that. You can see it on the table above your table 5, you see. So it's a lot more dense here to the left than it is to the right. It's less dense to the right. That's why, as you see, the distance here is much larger than to the left, where it's a lot more dense.